So my name's Joe Berg. I'm with a small private consulting company, Biohabitats, headquartered in Baltimore, but we have offices spread around, including New Jersey / New York. They live in New Jersey, but the office is in New York. And I've been spending a lot of my time looking at wetlands, floodplains, and streams. And my background is in systems ecology, so rather than looking at it purely from like a natural resource or a conservation ecology perspective, I'm looking at it more from a systems perspective, looking at those resources. And I'm the practice lead for restoration for this company that's got about 60 people. So I'm really focused on restoring these resources, trying to conserve what we have to start with, but trying to fix the resources where possible. So this is the kind of material that I'm going to be covering today. And so we'll just start with a little bit of background on the water resource issues. So, our pattern of development, our houses, our farms, our cities have dramatically changed the hydrology of our watersheds. So we're shedding a lot more water, and we all know this. And the way that water works in a channel is to create a channel that's large enough to convey that water. So if we're increasing the amount of water that we're shedding, we have to necessarily increase the size of our channels. And the only way that that occurs is through erosion. And here's examples. And in some cases, these weren't streams. These were just outfall locations. And now they've been sized down into the groundwater table, so now they are streams. This is a perfect example. This is Mount Vernon, just outside of DC, on Park Service property. The Park Service put in a pipe underneath of a hiker-biker trail, a nice little asphalt trail, through the woods, no houses, but a parking lot for people who were pulling in to use the hiker-biker trail. So this pipe caused about a 30-foot incised channel where the pipe outfalled, and this was sort of getting down to the floodplain of the Potomac River where that topography leveled off. This is an 84-inch diameter tulip poplar tree. So first thing, it's been there for a long time, and tulip poplar don't do very well in wet areas. So this wasn't a wetland. And I can walk underneath of this root fan. It's more than 5 foot because I'm more than 5 foot tall. Just a little bit more than 5 foot tall, but that's, more than 5 foot tall. I could walk under there. And so this was never a stream, but it has stream flow now. Doesn't have fish, probably has some aquatic invertebrates because they're coming in through their adult stage. And so it has groundwater. Just another channel in Cobb's Creek in Philadelphia. I mean, that's 8 foot incised, no flow, no groundwater. This is just a lot of sediment that's just gone a few hundred foot down into Cobb's Creek, where it then flows downstream, fills in behind or up in front of dams. This was a swamp, bottomland forest, wetland in the coastal plain. Now it's quickly losing its wetland status because this is the groundwater table, and this is about a 6 foot loss of the groundwater resource. And of course that's shallow, so you don't really have fish in there. It's very hot in the summertime, and we have just, because of the lowering of the groundwater table, we have increased microbial metabolism in these typically nutrient-rich and organic-rich soils. Now the bugs, because they have more oxygen, can eat a lot more, and they release those reduced organic nitrogen compounds like leaf material, and they're releasing them as mineral nitrogen, which is what plants suck up to grow. So you actually have a tremendous invasion by non-native invasive species that weren't adapted to those low forest environments, but to disturb disturbance communities, things that can really grow fast and displace other things. So this incision, this down cutting that's being caused by stormwater releases more nutrients from the forest soils, and that all gets transported downstream to whatever the receiving stream is. Just a little background. Any new engineers in the room? I think we've just got one. Just, well, any new folks come in that are engineers, yeah. New engineers do it the right way. The old engineers have been the problem. The hydrograph that's represented by that A, that's the undeveloped forest condition. So, when it rains, you have a slow buildup in the water volume, the surface of the water, and then when the rain cuts off, you have a slow drawdown. The soils drain, the water finds its way very slowly off-site. In a relatively old development, anything prior to like 1975, 1980, this is your hydrograph. So no stormwater quantity control, no stormwater quality control. So now we're talking about Philadelphia and most of its suburbs. We're talking about every place where we all live, unless we're in new suburban developments. New suburban developments would have a hydrograph like C. And of course the difference is that this has been designed to get to the same peak so that you don't cause downstream flooding, but the total amount of water that's coming off is still greater, and that water is doing work, and that's what's causing that channel enlargement and erosion and transport of the nutrients and the sediments.
The end of your graph, though, if you're looking to which also you stay with D, I think a lot of people ignore that.
Yeah, it's a good point.
The end is your normal flows are just about gone because your spring water's gone.
That's right. You're losing perennial flow in our streams because most of the water coming off of this converted watershed is coming off in big pulses, big flows of water, and there's not near as much soaking into the ground or being held in the watershed and leaking out slowly. It's shed very quickly by a very simplified drainage network. And this just reinforces the point that I was making, that water works on the channel, and it's when you start putting the changes in land use and you start eroding your channel and transporting materials downstream, some of that material goes all the way down to the receiving stream, to the next channel down. Some of it is deposited in that stream that's being eroded, and that causes more erosion. So it's this positive feedback, and I have to be careful. I like to say negative feedback, because what's happening is you have this increasing spiral of feedback. So a little bit of bad causes channel erosion and transport of materials downstream. Some of that material settles in the channel and causes more channel enlargement than just the water causes. So that's increasing. So you have this positive feedback. A little bit of bad causes more bad. And then you have these 6 foot in size channels, and this time of year you have freeze and thaw, you have a reduction in the density of the soil, and it sloughs into the water. During the summertime you have a storm, the water comes up, saturates the soil, the water goes back down, the saturated soil, now much heavier, succumbs to gravity and falls into the channel. So that's this increasing negative process. And this is some work that Matt Condolf and others, where they've really looked at how our streams work. We all think about streams in terms of fish and bugs and perhaps wetlands and bird habitat, but in reality, many of our urban streams aren't working that way. Our urban streams are enlarging because of our changed hydrology and shedding that material and changing the whole nutrient dynamic, the whole habitat dynamic. And this is some work that I was involved with in Chesapeake Bay. This is largely work from Dorothy Merritz and Bob Walter from Franklin Marshall in Lancaster. And it really woke a lot of people up, because what they're showing, under an extreme condition is 10,000 foot of sediment every foot of stream every year. That's the erosion rate. That's how much sediment is coming out. Now that's an extreme, but if you start looking where all these bars are coming up, they're up in the 400 pounds per foot of stream per year. And we've got tens and hundreds of thousands of feet of stream that are giving up sediment like this. Doesn't have to all be in, getting impervious drainage. It can be getting drainage from golf courses. It can be getting drainage from agricultural lands. I mean, we're not really talking about the good forest condition watersheds. So we've got a lot more water coming off. We've got a lot more sediment coming off. And what's interesting and what's been ignored is that every pound of sediment that's coming off has nitrogen and phosphorus in it. And it's surprising how much, because many of the streams that we're looking at are cutting down through sediments that were delivered as a result of colonial land clearing practices and agricultural practices. So a lot of the old forested hill slopes, which had this really beautiful, nutrient-rich, tied up in organic nutrients like refractory mulch that the trees are making from years and years of root growth and shedding, years and years of leaf mulch accumulation and fungal plant material coming in there and working on that. So all that material gets washed down into the stream valley and buried in sediment. And now we're re-eroding that, and by putting more oxygen into that mix, like I was talking about before, with higher rates of microbial metabolism, we have greater rates of nutrient release. So a ton of sediment that's eroded from a channel, which is, it doesn't take very many feet of a channel to erode, to give up a ton of sediment. You're talking about like 1/4 of a pound of nitrogen and 0.025 pounds of phosphorus for every ton of sediment. And if you have a normal rate, say an average rate, not even average, a normal rate of say 300 pounds, you don't have to go too many feet to get 2,000 pounds, which is a ton. Now you've just released 1/4 pound of nitrogen, which is more than we want to use to fertilize our lawns. So this is the sort of the humor section of the presentation. So what we've done is we've simplified our drainage network. We've basically eradicated 85+% of our stream channels, our first and second order stream channels, which would be they'd have the highest density in the landscape. So we've just filled over them, or we've made them into gravel drains, or we've made them into pipe drains. In the city of Philadelphia, for instance, in Tookoonee area, 1/8 of the city of Philadelphia has no streams and is drained via a buried pipe network that is, combined with our sewer conveyance. So you can imagine if you have 1/8 of the city, every time it rains, that water's going into the system, overwhelming our wastewater treatment plants, causing these discharges, these raw sewage discharges. And you can walk up these systems. The one I'm thinking of south of the boulevard, you could back, if you could get a tractor trailer down there, you could back an entire tractor trailer into the outfall and not even see it. That's how tall, wide, and deep they are. So the first thing is we've simplified the drainage network tremendously by putting in smooth pipes, whether they're made out of brick or concrete or steel, generally much smoother than a stream would be. So that allows, first you've got all that extra water. Now you are facilitating that because it's got a shorter flow path. So it can pick up speed and it can do some work. So it can pick up and carry more material than it could previously. So one of our ways of dealing with it is to make the material that the water flows over more resistant to erosion. So, concrete trapezoidal channels, which, groundwater freeze thaw, poor construction materials, low bid contracting, or just life of material. They always fail. Or you can't run them all down to the ocean. This is 9 Mile Run in Pittsburgh. You know, you just can't go far enough. And if you start to look at you know, the line here, this was the old surface. That's where that water used to be up here. And then you can also look just at how that pour for the concrete for this. So, you know, you've had 25, 30 foot of incision since the 50s. And that's not a big surprise. This is an engineering dream, you know? I mean, isn't that beautiful? That is so, it has natural curves, you know? It's made out of natural materials. And this is a real savings, because rather than using big rocks, you can use small rocks inside of chain link fence material, and it performs like a big rock, so it's much cheaper. So unfortunately, it doesn't have any water in it. It doesn't have any fish, and probably the only bugs would be chironomids and mosquitoes. Maybe that's probably not true. There's probably some other tubificids in there and all kind of issues. So getting to the talk, you know, when we do stream restoration, instead of using that concrete trapezoidal channel to fix a channel in place, we can use rock. It's a little more expensive than gabion, but we can do that, and that fixes the flow path of that channel. You know, when I look at this picture, I say, well, we probably didn't need to do that. But for all I know, you know, there's a big stormwater outfall here, and this is a step to armor this prior to all that extra water coming down the system. So this could be a reasonable management approach. It's not ideal. So here's one where part of the solution was making it wider. This is in Delaware, and the idea was to provide a flood-prone area so that when the stage comes up, instead of forcing that to flow in this U-shaped channel, which is what the incised channels are always going to look like, they're going to be U-shaped because those channels are going to erode to provide the greatest flow of water through the smallest possible cross-section. That's work. It takes extra work to make that channel erode wider, so initially it's not going to do that. It's just going to keep working to build that U-shaped channel. So this is giving you sort of like, if you can imagine it, more of a check-shaped channel with the bulk of the flow in that deepest part, and then an area out here where the water can expand as the stage comes up. You know, you've got some habitat and roughness elements, so this might have some habitat value. You're not doing anything for holding water, because the way that this is designed, if you think about the profile, which is how the water is flowing down this way in the stream, how it's flowing downstream. These are typically designed to have a fairly homogeneous slope. You know, if we were doing a sidewalk or if we were doing a patio, we might talk about a 2% slope. That's how streams are designed, to have this homogeneous slope. So when you do have a stage build up, it rises, it wets this area, so there's a little bit of water loss through soil wetting, and it does slow the water down a little bit because it has this wider cross section, but it has positive drainage. That as soon as the spigot gets turned off, as soon as that rain event stops, this water is going to go right back down because all the water can just move right out of the system. Even if it moves a little bit more slowly, it still facilitated drainage. So this is a conveyance channel. It has these flood benches, which is good for attenuating energy, but it's basically sediment in, sediment out, because you don't want sediment accumulating, because that'll cause channel migration. So this is a conveyance channel designed and constructed under the theory that you're working with an equilibrium with your sediment supply. Sediment in, sediment out. So you know if you're transporting sediment that way, you're transporting nitrogen, phosphorus, oil and grease, whatever else is being delivered is flowing right through the system. And this is a shape like this, which is better than a U-shaped channel, but only half. Oh, so I forgot I left this in. I was supposed to do a little bit more. So this is a project that Land Studies, Dorothy Merritt's, the EPA, and Elizabethtown, a whole bunch of folks in Lancaster have been involved. This is Spring Valley. I think that's what it's called. Is that right? Does anybody know?
Big Springs.
Big Springs, yes. So this is a beautiful system. What they did was they excavated the floodplain to get so that the stream would not have to, if the stream did rise, it could spread out and occupy this flood area, which turns off the velocity, turns down the velocity, drops the sediment, allows a lot of material processing, sort of activates the natural resources to do the things that the natural resources have always done. So if you think about it, nutrients are a resource. These systems have developed to capitalize on every bit of nutrient that they can get their hands on. There's no natural system that just allows tons of nutrient to escape. I mean, it all gets used up. When the salmon swim upstream and spawn and die, all that salmon flesh is used in the system. It doesn't wash down to to Philadelphia to pollute the water. That's all getting sucked up by the system. This is another kind of stream restoration that Art Parola from University of Louisville is doing. So if you imagine in Kentucky, they have issues with losing streams. You could be walking along this beautiful stream and then it hits this area of a limestone cavity. The water goes into the ground. It might go 30 foot, it might go miles. It pops back out again. So that's the challenge that he's been working with, and what he has found is by reconnecting the groundwater to the stream and not allowing these pulsing flows from stormwater runoff, put them back out on the floodplain, just the same way that Land Studies project that I showed in the previous slide did. So we have sort of a convergence of design. These aren't conveyance channels, these are material processing channels.
Excuse me. Are those, just out of curiosity, in Kentucky, are those sinkholes related to strictly stormwater, excess stormwater runoff, or is it partially from acid mine drainage from coal?
Well, it's even more than that. It's a natural geologic formation, but when you start shedding more water, you can start enlarging those routes. And we have them here. You don't have to go but one county west of us and have.
Lehigh County too has had terrible problems with sinkholes across the block.
Yeah. I mean, I had a project on one of the naval stores in Mechanicsburg, and they had a site that's parking lots for the most part, outside storage lots, lots of PCB containers stacked on the ground. And this was before they were outlawed. And so they had PCB contaminated sediments being shed, going right into a sinkhole, and then upwelling into Trindle Spring Run, just half a mile downstream. So, I mean, this is real. So regenerative design, this is the stream channel, this is the floodplain connection, and this is, so you have Land Studies working on their ideas, legacy sediment excavation to get floodplain reconnection. You have Art Parola working on his studies, using a lot of wood, using undersized channel design, which is floodplain reconnection. And you have people in the Bay Area, the Chesapeake Bay Area as opposed to San Francisco Bay, working on regenerative design where we fill the channel to get back to the floodplain because we don't have all that area that we can excavate, because it's typically highly valued stream valley forest resource. So a couple of years ago, this document, it would ignore the ability for stream restoration projects to modify the hydrology and the hydraulics. They said, this is important to understand, but stream restoration can only start with the geomorphology. There's nothing we can do to modify the hydrology or the hydraulics. has to start with morphology. You can't hope to have good biology if you don't have these foundation elements. And then this is a simple representation because there's feedbacks. You know, if you modify the hydrology, you're going to modify the hydraulics, you're going to modify the morphology of the channel, you're going to change the water quality, and it works both ways. You can have burrowing mayflies, which could modify the physicochemical because you have increased rates of hyporheic flow and exfiltration into the bottom of the stream through all their burrows. So this is a great document. This is how, rather than reference reach as a foundation for design, you know, think about this. This is more process, this is more system thinking. This is more of the solution for our future rather than repeating this stuff, taking it off of the shelf. And so this is where we start talking about some of the benefits. So because of the regenerative design and because of land studies and because of Art Parola and because of Dave Rosgen, there's been big efforts underway. There's been lots of criticism of the performance of stream restoration. Folks like Margaret Palmer from University of Maryland say, I've looked at thousands of stream restoration projects and none of them work. And then you have other people who say, here's 3 monitoring projects that I've done and we've got tremendous benefits, tremendous improvements. So this was a process of going through all the available literature and coming up with how these streams really perform. The first conclusion was we need to do a lot more monitoring because we don't have the robustness of the data. There's not enough data to be, you know, completely comfortable in our management and our prediction of how well stream restoration projects work. But there's enough to get management better than we've had it for the last decade. And that is, you know, if you do that conveyance channel, all right, and if we say, okay, so the data tells us we're losing 300 pounds of sediment per foot of stream under these erosion scenarios, if we do a conveyance channel, if we armor it, we should be able to reduce the sediment that's being exported from the site. So that's this prevented sediment during storm flow. So you have this eroded channel, you put rock toe walls so that the channel can't migrate, maybe you lay the banks back, you put grade control structures across the invert of the channel so the channel can't incise anymore. So for that 1,000-foot reach that you're working on, you're not shedding any more sediment or very little sediment. So that's this protocol 1. Protocol 2 is recognizing that there's a relationship between the water in the stream and the water that gets out onto the floodplain and has return flow subsurface into the stream. So that's this hyporheic processing. That's a nitrogen reduction credit because, you know, nitrogen is cycling and it doesn't go away unless it goes through the denitrification process. Then it's exported from the system. So this hyporheic processing drives denitrification, which is taking nitrogen from either a mineral form that plants can take it up or an organic form like urea where plants can take it up and putting it into a nitrogen gas. The atmosphere is already, I think, 78% nitrogen. So this is just a big part of the process. And there's things that you can do in stream restoration to get bigger denitrification rates. And that sort of goes to this second protocol. And then the third is this floodplain reconnection. So if you get the water up out onto the stream, you get some storage, you definitely get more surface area to volume. So rather than having that U-shaped channel that we talked about where this conveys as much water as it can, these channels, like the ones that I was talking about that Parola is doing, are undersized so that every time it rains, even if it's a 1/4 inch of rain, that water can move outside of the channel into the riparian zone. If you have a steep slope valley, it might only wet 5 extra foot on either side. But it's wetting that, which means there's water loss and there's resistance to flow because of trees, because of vegetation. So all that works with this floodplain reconnection volume. And then this protocol 4 was excerpted taken out of this, because it's really not a stream. These are typically the gullies, like the first slide that I showed, where you had a pipe and then you had an incised system below it. So this is what they look like, armoring, in-stream denitrification, where you basically, another way to think about that is a stream and wetland mosaic, where you're bringing that water up and you're saturating the riparian zone, so you're really doing a lot for wetland resources as well as the stream resource. And then floodplain reconnection, where you get all of this and you also get additional storage. So you have all these vernal pools, all these low-lying depressions that aren't necessarily well connected, that hold water, and then when the stage of the channel goes down, when the rain turns off, that water can't get out very quickly. It might have to infiltrate, it might have to evaporate. So that does a lot for attenuating the hydrology and the hydraulics of the channel. And that's been ignored until the last few years. So this is from the Bay program. So this is focused primarily on parts of PA that drain to the Chesapeake Bay, Susquehanna River. And just, look at the incredible opportunities here for stream restoration. These are really, this was an effort that came out of Maryland, so it's Maryland centric. So we knew more. We had better connections with accountability for what permits were coming out, what all the different county whips were requiring to meet their MS4 permits. So we got really big numbers. But this is like Jeff Haramf and some others from Pennsylvania DEP that informed this. Still tremendous increase in the stream restoration opportunities. One of the challenges, and I don't know how many people are concerned about folks using stream restoration to meet MS4 goals. Yeah, me either, but some people are really concerned about it. The idea is they don't want to be modifying our stream resources to trap sediment and nitrogen that's being dumped into our streams from, like, the mall or from churches and schools or other institutional facilities that have 30, 40 acres of impervious parking and roof area. So folks at some of the regulatory agencies were saying, well, let's put the brakes on here. Let's put certain restrictions, like repairs. Like if you have to go in and PWD wants to fix a section of a stream because it's eroding into their sanitary sewer line, that's not stream restoration. That's infrastructure repair. So that doesn't count. You can't take any credit for that. If you have a mitigation project, somebody's, the DOT has filled a section of stream or has to realign and shorten this, that you can't get a credit for that. You can't take a nutrient credit for that. You can't fix what isn't broken. All right, if it's a stream in good condition, it's off. Don't do stream restoration where you don't need to. So there's, I guess the point for showing this has gone through the Fish and Wildlife Service, the departments of the environment in Maryland and Pennsylvania and Virginia, West Virginia, Delaware. It's been adopted. All right, it's the real deal now. Most recently adopted in Maryland just this past summer, and just to give you a feeling, so for stream restoration, which is what we're talking about here, for every 100 foot, for every foot of stream restoration that you do, you can take an impervious surface credit. So 100 foot of stream restoration gives you 1 acre of impervious surface reduction. You can get these kind of nutrient reductions for every foot. That's what these values are showing. For every 1 foot of stream restoration, you get these kind of reductions. RSC, which is going to be sort of at the end of the presentation, gives you these kind of pollutant removal values. So that's like bioretention facilities, except it doesn't have a 1 acre limit. In this document, all of your stormwater retrofits have 1 acre limitations, unless they're like a regional pond, and then it's the design area for the regional pond. Those numbers that we saw, They were generated by the counties who were saying, okay, we have this MS4 goal and we have to drive these numbers. We have to get hundreds of pounds of phosphorus reduction in our county alone. How are we going to do that? Well, they look at, well, we have all these existing old style, like 1980s era detention ponds, extended detention ponds, and we can go into those because we own them, we have control over those, and we can retrofit those to get some of those pounds of phosphorus reduction. And as they started to look at that, they started coming up with some pretty big numbers, like $250,000 a ton for sediment reduction using those kind of basin retrofits or bioretention facilities, rain gardens, et cetera. Whereas $13,000 for a ton if they use stream restoration. So stream restoration may be the most cost-effective solution for these counties to be able to meet their MS4 permits. And I mean, it's compelling. You know, if you, this is one source, and these are pretty big numbers, and not every project's going to be the same. There's all these factors that you know, what is the drainage area, what's the impervious surface of the drainage area, how much sediment is being delivered, how long a stream restoration reach, because a short reach costs proportionately more than a long reach. This is another source. This is Center for Watershed Protection. And you know, they're giving numbers like nitrogen reduction, $260 per pound versus any of the other alternatives, which are an order of magnitude more, except for, you know, the no-brainers like pick up after your dog, or fix where a sewer is connected to a storm drain. You know, those kind of no-brainers. But for the most part, when you start looking at some of the retrofits, you know, it's a third the cost in this document of retrofitting a dry pond, which, you know, the county would think, all I have to do is go in, look at my barrel, change my outlet structure. So that's a pretty small effort. Cheaper to do stream restoration because you get more uplift with stream restoration. You get credit for 50 pounds of nitrogen or 50 pounds of sediment per foot, as opposed to, you know, maybe you get 50% reduction when you're looking at an extended detention or a detention basin. All right, so this is looking at some sort of a newer approach to stream restoration, that regenerative design. You know, if I was Mark from Land Studies, I'd be talking about excavating down to the invert of the channel adjacent to it in the floodplain. That's how I reconnect it. But you know, in DC and in Fairmount Park, in Baltimore, in Fairfax, in Boston, you can't do that. You can't go in and cut down 36-inch oak trees and excavate the soil from underneath of them to get a floodplain reconnection. So we bring the invert of the channel up, sometimes 30 feet, fill it, and then build an erosion-resistant conveyance system on top of it. Just a cross-section. So that was a profile. That's showing, actually, let's just make another point. We talked about how a normal stream restoration profile would have this sort of homogeneous slope, 2% slope or 1.6, whatever that slope is. That's the stream valley slope. That's the stream restoration slope. Here, we've got a series of flat slopes and then a short adjustment reach and another flat and a short adjustment reach. So the water can't get from this pool to this pool until it fills up every possible spot for storage above that. Once this landscape is saturated with water, then surface flow can continue downstream, as opposed to what's happening under this. If you put a gallon of water here, it's going to run, well, maybe not a gallon, but it's going to run downstream. It's going to be drawn down there by just this sort of homogeneous slope. Here, it has to fill and saturate every storage spot on the landscape before it can move to the next section downstream. So this is a cross section. That was the profile. This is the cross section, and it's just that simple. You know, this blue line is showing the groundwater prior to restoration. You know, it's basically you're losing all this groundwater, which means this is all well aerated, which means it's releasing a lot more nutrient than what it would if this. Now that you've got this up to here, this groundwater table comes up. And we've seen in a tributary to Cobb's Creek that we did about 15 years ago, in 2 weeks, we went from a 13-foot deep incised channel that had a little bit of seepage at the bottom to a perennial system, 13 foot higher in elevation. That means the groundwater came up 13 foot in 2 weeks. And we see that without exception. We see groundwater jumping up 4 foot in the most recent project in DC, which I'll show you some pictures of. So the idea is now this material isn't giving up as much nutrient. This material is not giving up any sediment. In fact, it's a reach that is holding sediment. Doesn't hold all the sediment because a lot of those fines are coming in. You know, on a small storm, you have a lot more hyporeic. A bigger proportion of the flow is hyporeic. On a large storm, you have more surface flow, and it's out in the floodplain where maybe it's ripping along at 3 foot per second, as opposed to if it was all in here, it might be ripping along at 25 foot per second. So it can't do the work. And all this is working to process the materials that are being delivered by that water. A real common question is, well, doesn't this thing get buried with sediment supply? First off, stormwater is generally very low in sediment. Most of the brown that you see from when you have a rain is from channel erosion as a result of that water. Water coming out of these pipes most often is clear. It's not carrying sediment. So whatever sediment is eroded continues to move downstream. It's not replaced. So you don't have a terrific sediment supply. The other thing is, and we've had some of these that are, like I say, 15 years old, and we really haven't had, we've surveyed them. We go out to these structures and survey them, and we haven't really had accretion of sediment. And when you start scratching your head, say, okay, well, what is sediment? It's a lot of calcium, it's a lot of magnesium, it's a lot of silica, it's a lot of iron, and they're all, with the exception of silica maybe, they're all nutrients for plants. So plants are actually withdrawing that material out of the sediment into their tissues, and then come the fall, they release the tissues, which creates a peat material that has elevated calcium, iron, you know. So that soil that's coming in is actually food for the plants. It's not just this inert, and I know it's hard to think about that. It's not just this inert material that just keeps accumulating. It is consumed as well. So this is a brand new project that was just finished up in October. This is it's a system in DC. There's no stream above it. It's just an 8-foot diameter pipe that was just ripping. So exposed sewer, and it's a little hard to see, but you know, 5 and 6 foot high banks. There's that handsome dude, you know, and so standing beside a sewer box, all right, that terracotta pipe is going downstream and it's coming out of that box, and that box is precarious. I mean, it's got no footer anymore. It's getting ready to topple. This is after restoration. This is the same area where that sewer was. So that channel has come up 5 or 6 foot. And now, before you had a little bit of water in the bottom, but you might call it an intermittent channel. Now it's a perennial channel because the groundwater's come up 5 foot and it has to sit in each one of these before it can get down to the next one. Lots of wood, lots of water, lots of material processing, and not a lot of velocity. And we had the benefit of seeing this under several large storm events, 3.5-inch rains in the summer. And you see some water moving out in the floodplain, and you have some little bit of erosion because it's not all been vegetatively stabilized, but nothing like what would happen if that water had been concentrated in this flow path. Because in this flow path, it was moving at 25 foot per second. So we talked about attenuating the hydrology and the hydraulics. You know, this stormwater is pulsed. And if you're working in, say, a 1,000-foot section or a 5,000-foot section, you only have so much surface area to deal with. And even when you have it multi-stepped like that, you've got a flat reach and a drop and a flat reach and a drop, you still have water coming into your system faster than it can get out. So what can you do with that? So the idea is if you use your stream restoration riffles as grade control structures, you can create landscape features, large ponds, only during runoff events. During base flow events, this would just be, you know, a narrow stream flowing down. But under the big storm events, you're forcing the water to get to a higher surface elevation here, which can then hydrate this, what we call a seepage reservoir. And this yellowish pattern represents about an 18-inch layer of sand and wood chips that are mulched and laid on the ground surface. In this particular instance, we had a road and a pretty steep slope, so it was all vines and invasive species. So as part of the construction, it really wasn't a big loss to clear that and to lay this mat on the ground of material. So just check out that cross section, and that red line is doing this. You know, there's the seepage reservoir, here's the material that we placed on the existing grade, and here's the stream. So this seepage reservoir is tied back to a grade control riffle where you guys are sitting. That's what sets the elevation of that reservoir. The only way for that water to get out of there is to find a more laborious path than flowing down a channel. It has head, it has stage, so it pushes down through the sand material, which is dominated by native plants. In this instance, wetland plants, shrubs and trees, which grow right through this material into the buried topsoil beneath it. So this is a project site. This is the stream. This is the recharge. So this is flipped from the graphic, but this is a pool of water that's maintained at that elevation by a riffle grade control up here. So the stream flow comes in, the stage builds, the water flows around here. This is 18 inches higher than this. This water is 1.5 feet lower than that water, and it gets a little bit further down. So these can, you know, these have to be sort of designed in context to the stream valley slope of your stream. But basically what happens is this water, the only way for this water to get out is to filter through this sand into the stream. So you have all kind of interesting things happening here. We've had carp, 18-inch, 2-foot carp, run up this stream, get into that, and get eaten by river otter. This is in Annapolis. This is an urban system. And this is 10 years after construction. All right, so this is that sand. You can walk on it in the shoes that we have on now. The sole of your feet will be wet, but it's not going to creep up and soak your feet because it's, you know, the porosity of sand is such it'll draw the water up, but water's not going to sit on top of it because water's going to drain to the stream or it's going to drain. This is sort of the high point. Atlantic white cedar, yellow-eyed grass, alder. I mean, we like to call it a riot of reciprocity. You know, this is what I would characterize as positive feedback. You start something good, and all we did was put sand and wood chips out there. And look what we got. Well, we put in plantings as well, native plantings, but it has taken off and it's really gone gangbusters. This is what that recharge pool looks like after 10 years. It's accumulated a lot of organic material, and it's really a beautiful wetland system. If you walk down into this site, you flush a wood duck, the wood duck will fly 200 foot downstream. This is only an 800 foot long site. You walk down to where the wood duck is, it'll fly 800 foot upstream. You walk upstream, I mean, it's a game. I think they're playing with it, but they don't want to leave the site because it's got such great habitat. So this is an ephemeral system where it's like the gullies that I showed in the first slide, you know. So what we are doing is filling the channel with this sand and wood chip mix and running water over top of it in this repeating series of riffles and pools, riffles and pools. So you have a lot of roughness, you have a lot of storage along the flow path. This is changing the hydrology. No, two. This is just a series, probably, I hope, familiar to some. I hope not overly redundant. So an erosion gully, it's been filled with a sand and wood chip. Here are the structures. You know, believe it or not, this is a 3-foot deep pool. You know, when the depth of field doesn't help you see that, but this is coming down 20 foot through that kind of a control system. And that's less expensive than doing cast drop structures. So it was less expensive to do that than it is to do this. And it has a smaller limit of disturbance, you know. That's 100 foot. This is 14, 15 foot. And it's cheaper to build because it's flowable material. You don't have to, you know, when you're putting these buried pipes in, you have to lay a bed. You have to put the pipes together, and you don't want differential settlement because then you'll have some subsidence, then you'll have cavities forming, and you'll have infrastructure failure. So you have to take extra measures with this, plus you tend to have to work inside of a box, a steel box. So you have to have a lot more material storage. This is, you know, it's a good solution. I'm going to go through this quick so that I leave time for questions. But so one site, we calculated how much we're going to raise the groundwater table. We calculated the storage potential in that overlying soil, how much water could we store, and then we let it out. And what we got was it extended the perennial flow in that channel by almost 3 weeks, which is enough for a trout stream, for this particular trout stream, to have reproduction 3 years out of 5 instead of 1 year out of 5. We didn't solve the problem, but we went in the right direction. That hyporheic flow and nutrient processing, denitrification, improvements to the incised wetland hydrology by raising the local groundwater table, and suppression of invasive species. Doesn't mean they're all going to die overnight, but it means you don't have to work so hard to get rid of them. So this is just the peak discharge and the restored reach versus a paired watershed. I mean, same drainage area, essentially the same land cover use, a fifth of the peak discharge. So a dramatic reduction in peak discharge and a dramatic increase in the time of concentration, the duration of that hydrograph. This is a site which had a conveyance channel, one of those U-shaped channels, about 800 foot long upstream, and a regenerative channel about 800 foot downstream. And look at the red is the outfall, the outlet of that normal channel design, that conveyance channel. So it's not doing anything to attenuate peak discharge. So in this case, that functional pyramid that I showed, they were right. A conveyance channel isn't working on the hydrology or the hydraulics, it's only working on the morphology. So the regenerative channels dramatically reduced the peak discharge. The point to show here is how important a 1-inch precipitation event is on an annual basis. It represents more than 90% of the annual storm events, a 1-inch rain. This is comparing a restored RSC to a paired watershed. Again, same drainage area, same land cover. And what you see is for storms up to that 1-inch precipitation event, which again represents 90% of the storms on an annual basis, there were 36 runoff events in the control stream and only 11 in the design stream. So that's a tremendous reduction. So that's affecting the hydrology, that's affecting the hydraulics. And this is just during Sandy, you can see this is the peak discharge for the reference system, the same as the last slide. Here it is for the restored system. So tremendous attenuation, even on big storms, almost 7 inches of rain. And then this is just looking at some phosphorus and sediment loads, and it's basically the same pattern. You know, you have a tremendous reduction even under really big events for phosphorus discharge. This is where the data doesn't really have the robustness to answer a lot of the questions. There's so much variation, especially when you start looking at speciation of a very active material like nitrogen. Works really well on attenuating temperature, so reduced the variation of temperature, reduced the absolute water temperature. And this one's flipped. The restored reach is in red. All right, so with that, any questions?
Slides available?
Yeah, I mean, I think we put them on the desktop, and maybe they send out an email and say, can we use them? And we say, yeah, absolutely. So I think they're posted to the website. Yes. So.
One of the problems that we've had is when a fix is suggested, a lot of the people around it are not interested in that wild-looking thing. They
Yes.
want a mowed lawn.
Some people have said it actually improves property value. You know, we haven't done that analysis, we haven't looked at it, but if you have a system behind your house that has a 36-inch pipe under it and its invasives dominate it, and every once in a while the county drives across your lawn because they have the right, they have the easement, and they mow it maybe once every 2 years or 3 years, whenever they get around to it. I mean, that's not an amenity. These things behind your house are amenities. They have water, they have birds, you know. So, not too much trouble with you know, the engineering mentality wanting those blocks lining their stream. Yes.
So there's been a study that there's a correlation between predator populations and stream bank stability. So is there a huge push in the state for the reintroduction of predators?
No.
Keep dragging them?
No, and another thing to think about is, so the logic for that predator stream bank stabilization is reduced herbivory on the banks so that you basically have better root mass holding the bank together. These have no banks. We fill them up to the brim. And this is what the historical landscape ecology says our landscape used to look like. We didn't have U-shaped streams. We had these saturated flow paths where the water found a concentrated path, but it never, if the stage got big because of like a hurricane, instead of it forcing all that water to flow through that concentrated flow path, which is what we do pretty much today, it would spread out and it would saturate that hole and flow 200 foot wide rather than 30 foot wide. Yes?
From an industry basis, when you look at, like, for instance, materials design, you know, they're switching from cradle to grave to cradle again. Do you see that happening with engineering, with civil engineering and stormwater management? Is it starting to sink in? Literally, I guess.
I think architects are coming to the fore with a lot of building design, green building design, which is starting to entrain more engineers into that process. And those engineers work with other engineers who are doing exterior infrastructure, and they're starting to think about things. So the company I work for is about a third engineers, a third ecologists, a third landscape architects, give or take. And we partner with architects, landscape architects, and engineering firms. So yeah, I think we're seeing improvement. I mean, as a stream restoration design and somebody who puts these things in the ground, we beat ourselves up a little bit about how much freaking rock we put out there. You know, because that rock, it took diesel to get that rock out of the ground, and it's disturbing that site. So you know, we're very interested in moving more towards wood. And in a saturated, so I've gone out to one of these sites, 10 years old, dug a hole, pulled up some of the wood chips, and they're still bright yellow and smooth. I mean, they're not rotting. I mean, anoxia, that saturated material, preserves wood long-term. So we're hoping to be able to, but when we're working for a public works department, we have to be mindful. They want engineering certainty. You know, is this going to stand up to the 100-year storm? And when we're using 4-inch poles to hold a wattle to bring up the grade of the stream, we have to say, yeah, maybe. You know, because there's only so much you can trust the models. Yeah.
Yeah. How often do you try to look for sources of public money for your clients as they're needing to or want to do restoration of these stream systems?
A lot. I mean, just this last week, I was working on 3 grant applications for NGOs. We have to be careful because there's a lot of watershed groups, there's a lot of NGOs who have a lot of ideas about what they want to do, and not all of them will resonate with the grant folks. But
You work with non-NGO programs?
both. We work with watershed groups. We work 4 counties who have some of these goals to meet. Yeah, and we like to work for the community. In the Bay, there's a Chesapeake Bay Trust grant that's due later this week, this coming Thursday, which is about $1 million worth of stream restoration monitoring. And they've indicated they're going to give 2 $400,000 contracts and several smaller contracts for like literature studies. But the big ones are going to be actual problem-solving efforts. And so we're on a few teams with those, like with universities, with private consulting companies. Yeah, I mean, I'll tell you what, collaboration, that's the best part of the job. Working with people who come from a different place, have different ideas, you come together, you learn from them, they learn from you, and that's you know, much more satisfying than anything that I've been doing before that. Certainly more satisfying than hanging flags for a wetland delineation, as an example. Yes.
So what were the total costs for these restoration projects,
They-
and what's
they-
the O&M cost?
Yeah, so the O&M is,
Non-existent?
it has been, and it has always been. You know, the idea, and it's funny, you know, the National Park Service, we're doing some work for them, for the DC government, but on National Park Service property. And, you know, National Park Service gets nothing. It all goes to defense, or it all goes to some other, but the National Park Service, for their land improvements, they don't have much of a budget. So when we're doing something like we're converting a stormwater outfall into a bubbler, which is a way to reduce the energy even before it gets into your stream, they'll say, well, what about maintenance? And I say, well, you're not doing maintenance anyhow, what do you care? But then I laugh and I say, oh, it's no problem, it'll be fine, you know. So the cost for these things depend a lot on the length. The longer they are, the cost per unit tends to go down. The amount of coordination that's necessary, you know, is it going to be an easy spot to work because it's wide open, or is it really confined by utilities, you know? So, but I'd say the costs go from like $200 to $1,000 a foot, but rarely less than $200 a foot, and that's design and construction. Yes?
Have you ever used any root wads in place of
Yes.
rock and thing, and how did it hold up, and how you know?
Oh, we love it. We love it,
Yeah.
and not just so we use large trees as grade control structures instead of rock in some of these. In some cases, we dump rock on top. The one contractor that built many of these, a guy by the name of Keith Underwood out of Annapolis, he's a landscape architect. He's an artist. Can be challenging to work with because while he's sitting on his equipment and he's actually running, you know, the excavator, he wants to do certain things. And it's like, Keith, that's using twice as much material. We don't have the budget for that. He's, I'll eat it, you know, and he does it, you know, and then he comes back afterwards. I used twice as much material. What happened? So you know, there are those kind of issues, but we're slowly migrating him to use more and more wood. And you could, I don't know if you noticed how much wood was in some of those projects. You didn't have the great seat there, but there's So a great story, this is a site in DC called Linnaean Park, which is at Linnaean and Fessenden, or Broad Branch Terrace and Linnaean. But he actually chased down like Asplund type contractors who had 8-foot diameter street trees. These are old silver maples that were being taken off of the streets because they were buckling the sidewalks and the road. And he gave them $100, and they just kept coming back because they'd have to pay to get rid of that stuff. And here's a guy who's giving them $100. So he just chocked that site full of, he split them, he sawed them, he drug them around on the road to flatten them, he made bridges out of them, he made park benches, he made park tables out of them. So, you know, really lots of wood. And that's a carbon source, and the people who live around it use it. You know, you go down there and you see names written in it with a Sharpie, which is a lot different than what I did when I was a kid. You know, but I guess because of that prohibition against carrying penknives in schools, they have Sharpies now. Well, I appreciate it. I used up all my time. Thanks.
Thank you.